Hey guys, so this is the video for Investigation 3, which covers the concept of continuity. And this is in the section 2.5 in the textbook. Uh, Sorry, it's like the mirror is having a little issues. There we go. Okay, pardon the technical difficulties. So the purpose of this is to understand continuity. And in order to understand this, we're just going to start with a kind of like down-to-earth question, which is, has there ever been a time in your life when your weight in pounds was exactly the same as your height in inches? And to explain your reasoning. So when you start to think about this, you might think about some extremes, right? Like, what was your height and weight when you were born? And then what was your height and weight now? And then we can think about all of the times in between. So when we were born was probably when we were the smallest and the lightest. So let's assume, correctly or not, that at birth our weight was about 8 pounds. You know, you might have weighed 6 pounds or 10 pounds, but it's going to be somewhere approximately that much. And then let's say that your height at birth was approximately 18 inches. Okay, so you might have been a slightly longer or shorter baby, but you wouldn't have been too much different. And I think that the important point is that when you're born, your weight in pounds is less than your height in inches. But then think about now, right? So we all have different weight and height. I can do mine like as an example. So my current height, I'm not too tall. I'm 5'4". So in terms of inches, that's 64 inches. And then my weight, well, whatever. Let's say it's about 120 pounds. Okay. Now, like I say, we all have different height and weight, but I suspect that for all of us, our weight exceeds our height, right? We all weigh at least 100 pounds, I would think. So, yeah, that's kind of like what's going on here. And if you want to think of this in terms of a graph, which we often do in the calculus class, I can try to make a sketch of something over here. So we're going to let's put on the x-axis, we can put our weight in pounds. And then on the y-axis, we can put our height in inches. And then we can plot these 2 points that we've determined would be on the graph. So let's choose an appropriate scale. Since everybody's weight is probably at least 100, maybe I'll count by 50s. Okay, and then on the y-axis, let's use the same scale. I'm just choosing to do that because then it might be easier to determine when they're the same or not, right? So basically, you know, the question of if your weight and your height have ever been the same is the same as the question of whether the graph of the function that we're talking about ever intersects this line. So this dotted line that I'm drawing is supposed to represent the line y equals x. So like 50, 50, 100, 100 will be on that line. Sorry, that looks terrible. Let me try to draw it again. Okay, so we're talking about this line, which is the line y equals x. So that would mean that height equals weight. So we also have these 2 points that we had talked about, right? So we have the point 818, which is maybe around here. This is my birth height and weight, and then I have my current height and weight, which is 120 and 64. So let's say that 120, 64 is here. And so we have like some function, which will be in black, and we have 2 points on the graph of the function. And the question is like, what is that function going to look like? Or in other words, can I connect these dots in any way possible such that it doesn't cross the pink line? And it kind of seems like no matter whatever I do, then at some point, such as like in my picture here, they're going to cross, which would mean that the answer to the question is yes, there was a time when your weight in pounds was exactly the same as your height in inches. And so why is this an introduction to the concept of continuity? So we could kind of like describe what it means for a function to be continuous. Really, it means that it's smooth with no jumps or breaks, such as your weight and your height in relation to each other. You can't just have one spring up, right? It just doesn't happen that you would have a break like that. It all kind of happens gradually, whether it happens fast or whether it happens slow. So intuitively, to describe what it means for a function to be continuous, we can say basically like that the graph is smooth with no holes or breaks. Another way that you can think about it, just like intuitively, is that maybe we could draw the graph without picking up our pen from the paper, okay? Such as the black graph represented above. And we're going to have a mathematical definition of continuity later on. This is just kind of like our first idea with like a real life example attached to it. So this next question, question 3, asks to demonstrate by sketching graphs at least 2 examples of functions that are not continuous. So try to think of different ways in which a function might not be continuous. And by the way, functions that are not continuous are called discontinuous. So, I mean, the hint is almost like in problem 2, instead of drawing a smooth graph, we could draw a graph that had a hole in it, or a graph that had a break in it. And so you can kind of think to yourself what that might look like. Okay. By the way, we'll go into the 3 common types in the next problem. There's also like crazy ones in the book that you'll see that are like oscillating, but I'm just going to draw maybe like one example, and then you can try to think of one on your own. So let's say I have a function that, you know, has a hole in it, and then maybe I also have a function that has a break in it, right? So this function fails to be continuous at 2 points, right? Or you could draw 2 different graphs as you wish. This is just kind of like the first type of example of a function that you can see where I had to pick up my pen off the paper to draw it. So you can think of other examples as well. Okay, so moving on, we're going to consider a function, let's call it f of x, that's discontinuous at x equals 3. So this is just making it concrete, but there's nothing special about 3. We're going to sketch 3 graphs to demonstrate the 3 different ways in which this function might be discontinuous, which is like basically the hole can be 2 different kinds of hole, and then the break is there. And we're going to describe the discontinuity using limit statements with the goal ultimately of creating the definition of continuity, which will involve limit statements. So the first type of graph, let's just make it like more specific with the scale on the axis and stuff, is, so I know that I want to focus on x equals 3, and the y-axis, it really doesn't matter. I can do whatever I want, but let's say I'm going to have a line that has a hole in it at x equals 3. So this would be like one type of function that's not continuous. We can just say that this is 5 just to make things concrete so that we can actually use limit statements. And now, it doesn't matter whether 3 is just like not in the domain of the function, or maybe 3 is in the domain of the function, but there's a different y point. Okay, so whether that is there or not, it doesn't matter too much. And this type of discontinuity is called removable type. The reason it's called that is that if I just basically took that bottom point away and moved it up and plugged the hole, then this would be the graph of a line, which would be continuous. So I can remove this discontinuity and find what's called the continuous extension of the function just by redefining it at one point. Okay, so what we see happening, and like really the reason why this isn't continuous, is because in terms of limit statements, the limit as x approaches 3 of f of x is equal to 5, right? As I get close to 3 but not equal to 3 on the x-axis, the y values are close to 5, but because there's a hole there, what's causing this function not to be continuous is the fact that f of 3 is not equal to 5. Okay, so this is kind of like how I would probably try to describe this in terms of limit statements. And like I said, this is removable, and then I'll just kind of make this as a note with continuous extension given by just the equation of the line. Okay, so that's the removable type. Another type is jump type. So this is, like I said, you could also have the whole, but what if the whole, what if the whole was there and then the function suddenly jumps up and then keeps going like that. So this is like, I can't just fix this by redefining it at one point. Okay, so let me like put the scale. So let's say this is 3. Let's say that this is 3 and then this is 4. Okay, so this is what's known as the jump type of discontinuity. It makes sense because the function kind of did like a little jump. And what I could say in terms of the limit statement, well, the limit as x approaches 3 doesn't exist. In particular, the limit as x approaches 3 from the left of this function is 3, and that's different than the limit as x approaches 3 from the right, which is 4, right? And 3 doesn't equal 4. So this function is discontinuous because of the fact that when we come into 3 from the left and from the right, we get something different. Okay, and then like I alluded to earlier, the other type of discontinuity that we can have is, what's known as like an infinite type. So when I actually have like a full-on break, such as a vertical asymptote, so let's say that this is what we have. This is just one example, but this is what's called an infinite type of discontinuity. And the way that we can describe this in terms of limit statements would be that the limit as x approaches 3 of this function is equal to infinity. So in other words, this function has a vertical asymptote. And by the way, in this example, f of 3 doesn't even exist, okay? All right, so now looking at all of these things, we kind of want to put them together to say, well, so what would we require of a function that is continuous? So we would need that the limit as x approaches 3 from the left and the right are the same, so that it doesn't have a jump. And also that the limit as x approaches 3 exists, so that it doesn't have an infinite. But even that's not enough, because as in the case of the removable, we have the limit as x approaches 3 of the function. It exists, it's the same from the left and the right, equals to a number, and yet this function is still not continuous because that limit doesn't equal to f of 3. There's a hole there. So if we kind of like take all of those restrictions together, we can come up with the definition of what it means for a function to be continuous. So I need the limit as x approaches 3 of the function to exist from the left and the right to be the same thing, and the thing that it has to equal to is the function value at 3. So this is the actual definition of what it means for a function to be continuous at the point x equals 3. And like I said, it's nothing too special about 3. So if it was any other number, such as a, the function is continuous at x equals a, if and only if the limit as x approaches a of f of x equals f of a. So this is our definition of continuity. And I want to note that this definition has 3 implications. Like, it's almost like so cute looking, it's like so compact that you kind of like lose something from it in a way. So when you see this, it means that, for one thing, f of a actually exists, right? Because f of a has to equal to a number. So that means that a is in the domain of f. So that's one thing that has to be true for a function to be continuous. So if a is not in the domain of f, then definitely f is not continuous at x equals a. Another implication is that, this is my next bullet point, the limit as x approaches a of f of x exists. It doesn't equal to infinity, it equals to a specific number. And for the two-sided limit to exist, both the left and the right limit have to exist and be equal to each other. So we know that the limit as x approaches a of f of x also exists, i.e., the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, okay? And like the third implication is just the definition again, but I want to restate it because, so this is kind of like the third implication, let me put it on a bullet point. The limit as x approaches a of f of x is equal to f of a. So you have the left-hand limit and the right-hand limit, and then you have the function value at the point. Theoretically, these are three different numbers. But in order for the function to be continuous, all three have to exist as finite values, and moreover, all three have to be equal. So, okay, that was the first video. Let me pause this, and then I'm going to create another video to go over the rest of the investigation.